Welcome to this video number 3, how to apply the filter coefficients in a first order active filter. So we'll actually look on how we design with these filter coefficients. Here we have a first order low pass filter design. We have the transfer function for it. You can see there is this passband gain, and we have only A1 as part of the transfer function. B1 is 0. We have two options with Opamps to design this first order filter. We have one with a non-inverting low pass filter, and we have one with a first order inverting low pass filter. And there are some specific concerns we have to do about it. But when we look at the transfer function for this circuit, we can see we have here the low pass filter, the passive one. That's actually the signal output from that filter is an input to the op-amp, and this is a non-inverting state, so it's simply gaining the output from the filter up and then put it out here. When we consider the transfer function of it, we can see that the general gain here is A0, so we can modify that to have a higher value than 1. And the resistors R1 and C1 is responsible for the cutoff frequency, and the resistor R2 and R3 are responsible for A0. So comparing coefficient to this one means that A0 can be calculated for 1 plus R2 over R3, and the coefficient from the filter is omega c, that's 2pfc times R1 and C1. If we compare to the inverting low pass filter, we can see that the capacitor is up here in parallel with R2. This is not an uncommon way to design a low pass filter, because it's just to parallel it, a capacitor C1. But there's a small note. We have this inversion, signal inversion, because we have an inverting filter, an inverting amplifier where the filter is embedded. And this sign here indicate that we have 180 degrees of phase shift coming from alone from the inverting amplifier, but the low pass filter adds another 90. So when we have 10 times over the cutoff frequency, we actually are up on minus 207 degrees phase shift. So this design adds considerable to the phase shift. But the transfer function is given by this, that the A0 here is R2 over R1 and the sign indication, and the coefficient for A1 is hiding behind here, and that's omega c R2 and C1 that are responsible for that. Yeah, let's have a small design where we actually find the coefficient. So normally we specify the corner frequency or the -3 dB frequency, or dear child has many names, and we have to specify the passband gain A0 and a capacitor. Then we solve for R1 and R2. We have already found that by solving, let's go back, these equations here we can solve for R1 and we can solve for R2 here when we know the capacitor. So For this setup, the non-inverting setup, we find that R1 can be calculated knowing the filter coefficient A1 and 2P and the cutoff frequency, the corner frequency we want. And we have to select a capacitor. Then after that, we can actually, based on our requirement for the passband gain here, select that size, subtract the 1 times it with R3, and R3 is one we have to select in order to get it further. So we can then calculate R2. A good selection for R3 can be anything between 100 ohm and 1 mega ohm, but here I think 1 kilo ohm would be fine. For the inverting design, we can again specify the requirements, but here we have only 2 resistors, so we don't have to select one value. So we simply have to specify the DC gain, and based on this setup, selecting the capacitor, the cutoff frequency, and having the coefficient from the Butterworth filter coefficients, we can just write a 1 here, and then 2p compared to what's cutoff frequency. We find R2, and then from that, knowing R0, we can calculate R1. So this is the very basic. Let's see it on an example. So we have here a design of a first order unity gain low pass filter. We specify the corner frequency to be 1 kilohertz, the DC gain to be 1, and 1 capacitor of 47 nanofarad. And we want to have it a max flat passband. So this is counting for an Butterworth filter. So we go in and use the Butterworth coefficient, our circuit, and since we have this information here, we can now calculate R1. We know A1 from the filter, it's a 1, and 2P, that's of course given for it. Then we have corner frequency of 1 kilohertz, that's this value here, and then 47 nanofarad, they are given here. Based on this calculation, we find out it's a 3.38 kilo ohm. Since we have a unity gain of 1, we select R2 to be 0 ohm because then it's just a buffer. And R3 we select to be infinite because we have to ground here an infinite resistance, air. And then it's just R1 and C1 we have calculated. That's quite easy. Thank you for watching this video number 3.